Big Bang. The fabric of our universe depends on just one number, which I call Q, which represents the ratio of two fundamental energies. If Q were even smaller, the universe would be inert and structureless. If Q were much larger, it would be a violent place, in which no stars or solar systems could survive, dominated by vast black holes. The sixth crucial number has been known for centuries, although it's now viewed in a new perspective. It is the number of spatial dimensions in our world, d, and equals 3. Life couldn't exist if d were 2 or 4. Time is a fourth dimension, but distinctively different from the others, in that it has a built-in arrow. We move only towards the future. Near black holes, though, space is so warped that light moves in circles and time can almost stand still. Furthermore, close to the time of the Big Bang, and on microscopic scales, space may reveal its deepest underlying structure of all, the vibrations and harmonics of objects called superstrings, which are in a 10-dimensional space-time arena. I've highlighted these 6 numbers because each plays a crucial and distinctive role in our universe, and together they determine how the universe evolves and what its internal potentialities are. These numbers constitute a recipe for a universe. If any one of them were to be untuned, there'd be no stars and no life. Is this tuning just a brute fact, a coincidence, or is it the providence of a benign creator? I take the view that it's neither of these. An infinity of other universes may well exist where the numbers are different. Most would be stillborn or sterile. We could only have emerged, and therefore we naturally now find ourselves in a universe with the right combination. It's astonishing that an expanding universe, whose starting point is so simple that it can be specified by just a few numbers, can evolve, if these numbers are suitably tuned, into our intricately structured cosmos. Let's first set the scene by viewing these structures on all scales, from atoms up to galaxies. Start by imagining a commonplace snapshot, a man and a woman, taken from a few meters away. Then imagine the same scene from successively more remote viewpoints, each 10 times further away than the previous one. The second frame shows the patch of grass on which they are reclining. The third shows they're in a public park. The fourth reveals some small buildings. The next shows a whole city, and the next but one a segment of the Earth's horizon, viewed from so high up that it is noticeably curved. 2 frames further on, we encounter the entire Earth with its biosphere seeming no more than a delicate glaze, and contrasting with the arid features of its moon. 3 more leaps show the inner solar system, the next the entire solar system. 4 frames on, a view from a few light years away, our sun looks like just one star among its neighbours. After 3 more frames, we see the billions of similar stars in the flat disk of our Milky Way, stretching for tens of thousands of light years. 3 more leaps reveal the Milky Way as a spiral galaxy, along with Andromeda. From still further, these galaxies seem just 2 among hundreds of others, outlying members of the Virgo cluster of galaxies. A further leap shows that the Virgo cluster is itself just one rather modest cluster. In the final frame, our galaxy would be a barely detectable smudge, several billion light-years distant. The series ends there. Our horizon extends no further, but it has taken 25 leaps, each by a factor of 10, to reach the limits of our observable universe, starting with the human scale of a few meters. Now imagine a set of frames zooming inward rather than outward. From less than 1 meter, we see an arm. From a few centimeters, a small patch of skin. The next frames take us into the fine texture